problems.
Okay.
And if we have time, some other section bank stuff.
Okay.
So yeah, I'll share. All right. Wait, wait, do you see my screen? You don't see the picture, right?
Picture?
Yeah, one sec. Do you see it now? Yeah?
Mhm.
Okay. Wait, actually I think I can get this. Okay. There. I actually have this open.
Okay.
So yeah, basically what gives me, I'd say, the most trouble in psych, it's the positive, negative, positive, negative, reinforcement and punishment.
Okay.
So there were two problems I got. This is the first one. I got it wrong. Just want to quickly go over it because I'm having a difficulty um basically seeing what's the stimulus and what's like the, response and all that.
Okay.
So for this, like we don't need to read the passage. It's like a pseudo discrete question. And should I like tell you what my thought process was or
Let me see. A divorced parent speaks negatively about her former husband in front of her child. This makes the child uncomfortable, and the child learns that if she praises her mother, the negative speaking ends. In this scenario, okay. What?
so yeah, here basically I remember what I was thinking is like if the child praises her mom, this negative speaking ends. So I was just like quickly like I saw the, if she praises her mother, the negative speaking ends. So I just thought, oh, you add something, um, and then it removes the speaking. So I put positive punishment. And so yeah, B. That's what I put.
Um, well, so okay, so yeah, if you're adding something, it's positive. If you're removing something, it's negative. If it's reinforcement, you want that behavior to continue. If it's punishment, you want that behavior to not continue.
Yeah.
So, okay. So if the parent speaks negatively about her, yeah, former husband in front of the child, that's the behavior, right?
Okay.
And if the child praises her mother, that negative speaking ends, right?
Okay.
So so the let's see. So the so okay. The thing that we're removing is or rather let's see. So the stimulus, let's see.
So, what do you think?
I'm trying to think what perspective we are thinking about in terms of negative speaking. Okay, so if we're talking about just that mother, that could be whatever, A or B, but praising the mother is the thing that the child is doing. So C and D would make more sense. Now, negatively reinforced versus positively reinforced. Let's see. Okay, so although we are adding praising one's mother, um, we are removing that, like the mother talking negatively about the former husband. So, so that could mean that if you are, yeah, if you're, let's see, I mean, okay, if you're removing the stimulus, I guess, of the mom speaking negatively, I think that would be the negative reinforcement because it's not like so so I guess okay, this can be tricky because either we can think of the child praising the mother as being added, or we can think of the child praising the mother as something that causes that negative speaking to end, in which case it would be negative, removing,
Yeah,
remove.
but how do I know which one to think of it as?
Yeah, that's the thing, right? So
Yeah.
I think that if we are trying to, okay, if when you praise one's mother, the negative speaking stops, you want to reinforce that behavior in which that negative speaking ends. So that would mean reinforcement rather than punishment. And then are we adding something or are we removing something? It seems like in the context of the mother, where the negative speaking is removed, that could mean negative reinforcement there. So I think that this question can be confusing because we can see like, praising the mother as something you're adding to it.
Yeah, which then leads to
Hmm.
speaking and
Yeah, so I think the proper way of viewing this is that the the undesirable thing of negative speaking, we want that to end, right? And if it is the case that praising the mother causes that negative speaking to end, we want that behavior of the negative speaking ending to be reinforced. And what we're removing is that negative speaking. So I think that I think that's the proper way of viewing it. Um, because okay, if I look at D, okay, maybe okay. So maybe the child praising the mother that leads to ending the negative speaking could reinforce this behavior of praising the mother, because I kind of see that now. It's the the behavior is praising one's mother rather than the negative speaking thing. So praising one's mother is we want that behavior to continue, so it's going to be reinforcement. Um, and then if we are stopping that negative speaking, I guess that would mean um, that we're removing that the negative speaking thing that we don't want. So we don't want the negative speaking to continue. So if you praise the mother, the negative speaking doesn't continue, and we want to reinforce that by having you praise the mother. And that should cause the negative speaking to end. So that's what we're removing. But yeah, it's confusing because I don't know if I should think about it in terms of, well, I guess C and D are from the perspective of the child. A and B is the perspective of, I guess, of the parent.
Yeah. Okay, so I was thinking of it from the child, basically from the perspective of the child. That's the
Oh.
goal here. Okay, next is this. Heroin addiction treatment programs often involve administration of a related opioid analgesic. Which one is it actually? How do you say this word?
I don't know how to pronounce it properly. Analgesic, analgesic.
All right, yeah. Such as methadone to reduce withdrawal symptoms. Learning theory predicts reduction of withdrawal symptoms by administering methadone. So, okay, you're administering methadone. That's the behavior, right? Or what? Wait, yeah. Administering methadone is the behavior. And that leads to a reduction of withdrawal symptoms,
Mhm.
which is negative.
Mhm.
So the answer would be B here.
Yeah,
It would?
yeah.
Okay, got it. So yeah, my issue,
So this
yeah.
so this can be confusing in the same way as that other problem in that are we adding is the thing that we're adding like the methadone that we're adding is that what we're doing? In that case that would be positive. Or are we adding that to reduce the withdrawal symptoms.
Hmm. Right.
So it's just like, so it's analogous to the previous problem in which the withdrawal symptoms is the mother complaining,
Right.
and the praising of the mother is analogous to the methadone. So
Right.
this actually makes that other problem make more sense now.
So, okay.
Because so this is methadone to reduce withdrawal symptoms, right? And that other
Mhm.
one would be praise to reduce negative speaking.
Yeah.
So, and that can be confusing because in both cases, we are either adding methadone or adding praise, which can lead us to choose positive. But we want to look at, I guess, first, what is the undesirable stimulus, right?
Right. So,
Mhm.
with negative reinforcement and positive punishment, are you using undesirable stimuli in both?
You said negative reinforcement and what?
Positive punishment.
Okay. Negative reinforcement, you want that behavior to continue because it's reinforcement. And if it's negative, you're removing a stimulus. So since it's reinforcement, you would be removing a bad stimulus.
Yeah.
Whereas positive punishment, positive means you're adding, punishment means you don't want you want the behavior to stop. So that would be like adding a negative,
Stimulus.
yeah. So here.
So you also, so basically you can also have a clue of what it is if like you're adding something bad
Mhm.
or you're removing something bad.
Mm-hmm.
But
Yes.
it, but it's like I can think of it as like adding methadone is a good thing, you
Uh-huh.
know?
Yeah.
That's why I put A on the exam.
Yeah. Yeah, I probably did too. So this is just like that previous problem. So we want to see it first from the perspective of the undesirable stimulus, right? The undesirable stimulus is what for this?
Withdrawal symptoms,
Yep. And for the other one,
negative speaking.
yeah. So we want that to stop. So that means that if we're thinking about it in terms of reinforcement, we want to reinforce the thing that makes that undesirable stimulus stop. So in this case, uh, if you have methadone use, right, you're removing that negative stimulus. So that is the negative reinforcement. And for the other one, it's praising your mother reduces the negative speaking. So that's why praising your mother for that other problem is also negative reinforcement. So think about it first, I guess, in terms of, an undesirable stimulus. Because if you have an undesirable stimulus if you have an undesirable stimulus, um, punishment can be done uh directly, but reinforcement would be done indirectly because whatever so like yeah in this case the methadone reduces the withdrawal symptoms, so we want to think about the withdrawal symptoms as or removing the withdrawal symptoms that as the behavior you want to reinforce.
Hmm. Okay. I think the main thing was removing the undesirable stimulus, I feel like see it from that perspective. Hello? Oh, yeah. All right. Do you hear me?
Yep.
Okay, good. Okay. Okay. So this is the next thing I want to do.
Okay.
Um, yeah,
So this is a new passage?
yeah, it is.
Okay. So why don't you start reading slowly and think out loud, and when you see buzzwords, acknowledge them, and I will interject um as well.
Okay. Um, wait, I'm just making sure this, yeah, this is the right passage. Okay. Um, the first committed step of galactose catabolism is by catalyzed is catalyzed by galactokinase, which transfers a phosphate group from ATP to galactose.
Okay. Tell me about buzzwords here. There's
Um, hmm?
uh I see three buzzwords.
Three.
Mhm.
I mean, I guess galactokinase,
Well, let's start with galactose.
galactose, yeah.
What is that?
Say sugar,
Okay.
um, six carbons.
Mm.
What?
Oh, wait. Sorry,
It's a
sorry.
sugar.
Yes, six carbons. Go on.
I mean, that's all galactose, yeah, it's like a similar to glucose, but like
Uh-huh.
it's one of the OHs is like flipped.
Is
Um,
something you could draw?
yeah, I could draw it for you.
All right.
What?
Yep. Go for it.
I feel like you right now.
Hmm. Okay, you do have it down. So, uh, you know, so okay, like, uh, like in I don't know if you learned this in psych social, but like how our brains work as like a network of like semantic nodes.
Yes.
So like that. So yeah, when you see something like galactose, I want you to like think about have all these other things come up. So like for instance, this is what it looks like, and other things would be like epimers, right? What's an epimer?
I mean, it's differs at one carbon.
One any carbon?
Uh, the reducing one?
Uh
I don't know, honestly. I just know that like mannose or mannose and galactose and glucose are all epimers.
yes. So an
I guess you could say they're the stereomers or no, enantiomers.
so
I don't know. You
yeah.
go on, yeah.
So an enantiomer, opposite stereochemistry at every chi
Yeah.
chiral carbon, right? And then epimer, it's exactly what you said, opposite stereochemistry at one, but you said carbon, and I wanted you to say chiral carbon
Oh, okay.
because what is required in order for a carbon to be chiral?
For chiral, four different groups.
Yep. So like, is this
No.
Good.
There's two H's.
Good, good, good. So now a diastereomer will be opposite stereochemistry at least one, but not all chiral centers.
Yeah,
But what if you have a diastereomer that has one, like opposite stereochemistry at one chiral center?
I guess that's an epimer.
So it actually, an epimer will only apply to straight chain stuff, not rings.
Mhm.
So if you have opposite stereochemistry at one chiral center and it's not a ring and it's a straight chain like this, that's an epimer. But if it was like a ring, it'll be a diastereomer.
Interesting.
Yeah.
Okay.
Now this so like what would I'm guessing like what glucose would look like. Like where how would that look like? You don't have to draw like a new molecule. You can just kind of tell me what changes.
In glucose, like this OH would be on the right.
Okay. So so that means that so which not like if you numbered the carbons, which carbon would that be?
Three.
Um,
That's my other issue. I sometimes like have issues with the carbons with like sugars. I don't know. I would guess carbon three, but
so what okay, so glucose. Oh, I see, I see. So okay, you're right, but this is the first carbon, second, third, fourth,
mm,
right? So galactose is a C4 epimer of glucose,
mhm.
okay? And there's also mannose, which is a C2 epimer of glucose.
Got it.
And yeah, those are the ones you're expected to know. So okay, good. Galactose. All right, what's catabolism?
Metabolism breaking down of something. Anabolism, you put something together.
All right, now and then tell me about kinases. There's all
Yeah, kinases, they're transferases. You take phosphate from ATP and you put it onto a molecule.
um what about the other way around?
All the way around is phosphatases, which are hydrolases.
So um okay, so a phosphorylase will only add phosphates.
Did I say phosphorylase or phosphatase?
You said phosphatase,
Okay.
but a phosphorylase will only add phosphates. A phosphatase will only remove, but a transferase doesn't necessarily do one or the other. Meaning you could take a phosphate from ATP and give it to the substrate, but you can also take a phosphate from the substrate and give it to ADP to make ATP.
Okay.
For instance, pyruvate kinase, last irreversible step in glycolysis, goes from PEP to pyruvate, right?
Hmm.
And PEP has a phosphate, pyruvate does not. So ADP gets the phosphate from PEP to turn into ATP. So you're not always adding a phosphate to the substrate for a kinase. You could also remove it.
Yeah, but a phosphorylase is a transferase too, just like a kinase, right?
Nope. So a phosphorylase will only add the phosphate.
Wait, so what enzyme classification is a phosphorylase?
Um, I think it's like a what is it?
I, because I searched it up and it says, I thought it was transferase, but, 'cause- I searched it up and it says, I thought it was transferase, but.
I think it's a ligase, but let me see. 'Cause I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase, but let me see. I think it's a ligase,
The internet says that it is a phosphorylate. It's a transferase.
Okay, my bad. So sure. Okay, so it's a transferase, but the phosphorylase should only add a
Hmm.
phosphate, whereas the kinase can also remove a phosphate. Okay.
Okay.
Now, what else is important about kinases?
Okay, kinases, what else is important about them? They take from ATP. I don't know what else.
Think about how it does that.
Adds a phosphate onto.
So like think about so like so we know okay it can take a phosphate from ATP and give it to galactose, let's say, but think about it on the molecular level, meaning
It takes it from the gamma.
gamma phosphate of the ATP, right? And what if you think about that molecule, what, attacks it?
Nucleophile,
Yep. And what would be the nucleophile?
like the OH group.
Good. So kinases need help from three amino acids.
Kinases need help from three amino acids. Yes, SYT.
Yep. Which are ser
Serine, tyrosine, threonine.
good. And they all have hydroxyl groups as their side chain, right?
Yeah.
Good. So, yep, that's it. All right, cool. Continue.
Analysis of the substrate binding pocket shows that various residues engage in hydrogen bonding interactions with galactose. Okay. Yeah. We just spoke about a couple of them.
What?
Like residues that engage hydrogen bonding. There's many different types in general, but um here they bring up arginine, glutamine, and aspartate, and glycine.
Any
That's
of them seem weird?
glycine.
Why?
Uh, because um it's like not negative or positive. It's just I don't remember the word. Um, but yeah,
Well,
it
is
has
that
no charge. It has no charge. That's what I meant.
sure? But I mean, is that the only thing I mean, does it necessarily have to be charged from what they're telling us?
No, it doesn't. And there was a question on this, which is why like
So,
I understand.
what does it need to have according to what we just
It needs to have nitrogens or oxygen, and the only place where glycine has it is like in its carboxylic and amine group. The
so
side chain of glycine doesn't have.
okay. So you're saying that it needs those elements because in order to do what?
In order to hydrogen bond
Good.
with galactose.
Yeah. So spawn, right?
Yep, yep.
So remember that like fluorine counts as well.
Hmm.
So yeah, the glycine doesn't have, at least in its side chain, something that, I mean, what is the side chain of glycine?
Side chain of glycine is nothing. It's hydrogen,
Huh? It
technically.
so is what is glycine going to be like a D or an L or something?
Um, well, it doesn't have like there's no chiral center.
Good. So yeah, it's achiral. And awesome. Yeah. So yeah. So if it indeed hydrogen bonds with glycine, it must be with the backbone, right?
Yeah.
There's another question in the section bank from like some earlier passage that said the same thing, but instead of the glycine, they said alanine.
Mhm.
And it was like the same thing with the backbone. But all right, excellent, good. So all right, continue.
Inhibition of GAL-K represents a possible treatment strategy for sufferers of galactosemia. a red genetic disorder caused by defects in the galactose metabolic pathway. Um, okay. While glucose is an effective inhibitor of GALK as it makes similar interactions with active site, researchers are interested in understanding GALK kinetics to aid in the design of non-natural small molecule inhibitor. Yeah, design of non-natural small molecule inhibitor molecules.
Okay. What type of inhibitor do you think glucose could be?
Glucose, competitive,
Oh,
active site.
huh? And okay, and then yeah, no, this is another thing you'll see tons of passages on. Like essentially they'll take the enzymes, sorry, the amino acids at the active site and turn it into something that's not important, like alanine typically or glycine or something like that. Um, and then evaluate the kinetics and see if the kinetics change a lot. And that helps us figure out which, amino acid residue in the active site is like really important. So, okay. So they're saying that glucose is okay. So first of all, galactosemia, what do you think that's about?
A lot of galactose, or maybe the opposite. I don't know.
So GalK does what?
Okay, Gal K transfer phosphate from ADP to galactose.
Uh-huh.
So
Ultimate.
first step, oh, galactose catabolism. You don't have,
Mhm.
yeah. So if you don't have galactokinase,
Yeah.
then you have a buildup of galactose.
Uh-huh.
So you would have a lot of galactose in your system. Right.
Yeah. So if they're saying that inhibition of GalK could be a treatment for people with galactosemia, that means that likely means people with galactosemia have too much, perhaps, galactose catabolism or too little galactose, right?
Mhm.
Okay, cool.
Okay. In order to study the kinetics of galactic catalysis, researchers coupled the phosphorylation of galactose with two other enzymatic catalyzed reactions. The coupled reactions were the pyruvate kinase catalyzed conversion of PEP to pyruvate and the lactate dehydrogenase catalyzed conversion of pyruvate to lactate.
Oh, yeah. So here we have the example that I mentioned with a kinase now removing a phosphate, right?
Okay.
From PEP to pyruvate, right?
Yeah.
So if you went into this thinking that the kinase only adds, once you get to that part, you can see, you know what? It could also remove, right?
But um doesn't P phosphatidylpyruvate to pyruvate, doesn't um that adds a kinase, right? Like I mean that adds a phosphate, right?
Well,
Oh wait, because you go from ADP to ATP, right?
so so PEP is the one that has phosphate. That's why it's called this, phospho.
Uh-huh.
So if we're going from phospho pyruvate to pyruvate, we're losing a phosphate, right?
Yeah,
But it'll go to ADP to make ATP.
got it.
Yeah.
Yep. Okay. That makes sense. That
So
makes sense.
So to study Galactate catalysis, they coupled the galactose phosphorylation, that first step or whatever, first committed step, with the pyruvate kinase reaction and the lactate dehydrogenase uh, reaction, which converts pyruvate into lactate. Um, And then they said the reaction was monitored by the decrease in the concentration of NADH. So, why would they use that as I guess, way to monitor the reaction?
Yeah, I mean, I was confused here because um, I know lactate dehydrogenase that it leads it go basically it has NAD plus get converted to NADH. It's a dehydrogenase, and usually when I see that, it's NAD to NADH. Um,
Yeah, but be careful because it things can go in the opposite direction with that same enzyme, right?
right. So I was a little confused. I mean,
Huh?
yeah, I don't know because
Yeah. So
yeah, I don't know.
yeah, um so if we don't have oxygen and we just finished up glycolysis, it would go into the lactic acid fermentation, right? To turn the pyruvate into lactate. Now, we need NAD plus for glycolysis, right?
Hmm.
So, and at the end of glycolysis, we turn that NAD plus into NADHs, right?
Hmm.
And the ultimate purpose of the NADH and FADH, like two or whatever, is to be is to ultimately give their electrons to the ETC, right?
Yeah.
But if you don't have oxygen, you're not going into the mitochondria, so you're not going to be you're not going to be meeting the ETC. So there's no point in saving NADHs to give to the ETC because you're not going to get in anyway.
Hmm.
So since the only other thing you can do possibly other than gluconeogenesis is more glycolysis, it would make sense to make more NAD plus so you can do more glycolysis. So pyruvate to lactate is actually going to turn NADH into NAD plus. It'll replenish the NAD plus supply.
Hmm.
So that's why they can monitor this reaction with by monitoring the decrease in the concentration of NADH,
Hmm.
right?
Okay.
So that's why it's yeah, the decrease. Okay. And then they say the resulting kinetic data with respect to both ATP and galactose are shown in table 1. The experiments were conducted using wild type GalK and then two variant forms where the aspartic acid was substituted with either alanine or glycine. So we're removing the charge, we're removing that specialness to it. And then I guess the only difference between alanine and glycine then would be size.
Hmm.
So let's look. Okay, table 1, gal K, kinetic data. Wild type gal K, K cat. What's K cat stand for?
Um, Turnover rate.
All right, cool. I thought you were gonna say, what do you think thought you were gonna say? Not you is like,
Catalytic efficiency.
yeah, yeah. Like, no, I don't mean you, like,
I was
specific,
about to say
but a lot of,
it.
but what is catalytic efficiency? What would that be?
I mean, honestly, no clue, but I'm basically a robot. I just know that it's KCAT over KM.
Yeah, that's all. That's all you need.
Okay, good.
Yeah, so we have KCAT, we have KM, galactose, KM, ATP. What's KM?
KM is it's the enzyme concentration at one half of the Vmax.
Close.
I guess substrate concentration.
Because
Yeah, that was something I was having trouble with when I was doing this.
yeah, so Michaelis-Menten assumptions essentially state that your enzyme concentration is, first of all, it must be way, way, way smaller than the substrate concentration. But also, if you think about like, a regular Michaelis-Menten, graph, like the x-axis is substrate concentration and the y-axis is rate, right?
Hmm.
So that means from left to right, you're increasing the substrate concentration, but we're not touching the enzyme concentration, right?
Mhm.
So Yeah, so it's a substrate concentration at to be able to reach 1/2 V max. Now, is Km like similar to the like the affinity? Let's say the affinity for the enzyme for the substrate, or is it?
Yes. Well, like lower Km is higher affinity. There's a relationship.
Yeah, what's that relationship?
It's inverse.
Correct. Perfect. Great, great, great. Cool. So we see, all right, some number, some number, some number. And then when we change that, we get a slightly smaller kcat, significantly higher Km for galactose, pretty much same Km for ATP. And then this one, we have significant, like a tenth of the kcat, and we also lower the Km, and oh, we have like a tenth of the Km for ATP as well. So that's pretty interesting. So yeah, that's pretty much, you just look at what essentially changes. Um, and yeah, that's pretty much it. So
I mean, this like I just know the ones I got correct. I don't know the
yeah, that's
ones.
exactly yeah. So
Yeah. So this is D. Like I just knew how to do this. I got this right.
yeah,
I
but
don't want to. I'm listening.
But when we first read it, like, yeah, you want to read it like that so you can anticipate questions like this.
Yeah.
Good.
Yeah. Now I do because I didn't even remember that Alan question actually from, and I
Hmm.
did the previous section in questions, but I guess I forgot it. But now I know.
Yep.
Um. Yeah. All right. So just a mental note, like glycine and alanine and like other quote unquote like basically amino acids that have like high, what's the term for like alanine, glycine?
I
If they
guess
have
like uh like what like thinking of like the maybe non-polar or something like that.
yeah, non-polar, there we go. Like they're technically non-polar, but they can interact with other molecules through their
Backbone?
backbone.
Uh-huh. Yeah, because
Okay.
peptide backbone is indeed polar, right?
Hmm.
Hmm.
Okay. All right, I'm just writing it down now so I don't forget later. All right. Here, uh, this was just knowing the formula catalytic efficiency. I got it right. Like, I just don't want to go over it or like waste time on it. Here, so it asks for the natural substrate of Gal-K.
Uh-huh.
Um, I got this right too.
Yep. And
Um,
like what we talked about when we first looked at it as well.
yeah, so galactose, mannose, and glucose, they are six carbon aldoses. Fructose is a five carbon ketose, right?
It is a ketose. Um, Let me
Oh
see.
wait,
I don't remember if it was 5 carbons or not, but
it might be six. Yeah, okay.
the thing with a what is it? The thing with a ketose is it makes a five-membered ring. So yeah, it's 6 carbons as well.
Got it.
But your since it's a ketone, your carbonyl group is not going to be at the first carbon.
Hmm.
So when it forms the ring, instead of it being a six-membered ring, it'll be a five-membered ring.
Hmm.
That kind of makes sense. Like,
Five. Wait, that's so there's also terms like furanose and puranose. Puranose is six membered ring, right?
yeah, you can think of it as furanose F starts with an F, so it's five, and
Hmm.
also fructose starts with an F, So, but
Hmm.
but yeah, so you'll get, something like this. So when this attacks that, it's closer, so it'll be a five-membered ring rather than a six-membered ring.
Okay. Is there anything that's a five carbon ketose or
Uh,
aldose?
Probably, but a five-carbon ketose would make a four-membered
Oh,
ring, and that has pretty high ring strain. So, you know,
got it. Got it. Okay. This is this is one of the ones that like I have trouble with.
okay.
So yeah. What
Most,
is
yeah.
should I go or you go?
Yep.
Okay. What is the most likely reason for the decreased KM values observed in D4-5G variant compared to the other versions of GalK with respect to each substrate?
Okay.
So I saw a decreased KM value, and in my head right away, I was like, okay, that means more affinity.
Yep.
There's
Hmm.
also less substrate needed. Yeah.
Hmm. Yeah. Less substrate needed to achieve one half Vmax, right?
Yes. But would the Vmax still be the same?
That's a good question. What type of, well, what other, can you think of any other scenario in which Km decreases?
You're saying in terms of like inhibition? Like,
Yeah. Mhm.
well, um, like uncompetitive inhibition, for example.
Yeah, yeah, yeah. And so Km decreases there. Anything else?
Vmax
What about it?
decreases.
Yeah. So that can help. Um, because like, it wouldn't really make much sense if so an uncompetitive inhibitor, an inhibitor is meant to make, make the enzyme not work as well. So why would it, I mean, if it's the case that it lowers Km, it seems like it would enhance it, right?
Yeah, the thing is like when I was doing this for some reason, I thought that like, there are like pictures where it's
Uh-huh.
like that. It wait, yeah, but also where it's like the Km decreases but the Vmax stays the same.
Mhm.
For some reason, I thought that would be the case. I don't know why, but like, I just like I don't understand what clue here
Yeah.
would lead someone to thinking it's uncompetitive inhibition.
Oh,
I just feel like it's
so yeah. So yeah, I don't know if it's uncompetitive inhibition, but I mentioned that to try to basically say this, that if an inhibitor lowers Km, that doesn't make sense because that increases the affinity for the enzyme and substrate, right?
Mhm.
So there must be something else happening here,
Oh,
Km to decrease. And it's because if Vmax decreases, which would make sense for an inhibitor, half of Vmax decreases as well. And if half of Vmax decreases, your Km would decrease as well, right?
yeah.
So I haven't looked at these choices yet, but that's the way that I would think about it. Because a
Mhm.
decreased Km on its own makes no sense. That should enhance the catalyst rather than inhibit.
Yeah, because you need less substrate for
Oh,
it to reach its
yeah,
like
yeah,
it,
yep. So, okay.
okay.
So the substrate binding pocket is too crowded. What are your thoughts there?
Um, that's what I put, and it was wrong.
So
So,
you're thinking.
because what I was thinking, yeah, it's I don't know. I guess for some reason, like maybe there's just so much of the substrate.
So the only difference here between the wild type and this, or rather, what are we doing? This one? What's the only difference here between these two?
Just like the amino acid at 45, the glycine.
Yep. So it's not like they have different substrate concentrations, right?
No.
So now if you go from anything to glycine, that gets smaller.
Mhm.
So it should be less crowded,
Okay.
right? Okay. Tell me about.
A key hydrogen bond between enzyme and substrate is lost. Like, like yes, that is true. But the thing is, if you lose a hydrogen bond, like if you decrease Km, that's good for the enzyme.
Mhm.
So why, like, that wouldn't make sense. Like, yes, it is factually true that if it goes from aspartic acid
Mhm.
to glycine, it loses a key hydrogen bond.
Mhm.
But wouldn't that make the enzyme worse?
Mhm. Yeah, because the hydrogen bonds apparently are what connects the substrate to that active site. So if we're losing that, we should see like a higher Km, right? So,
Yes.
but we don't see that. So that doesn't seem to be lost. Um, and then what about C?
The enzyme is unfolded as a result of substitution. If the enzyme is unfolded, the Km would be like infinite. Like it would be, it wouldn't function, the enzyme.
Um, yeah, I guess you can argue like, the functionality of the enzyme decreases and stuff, or rather the Kcat. I mean, you could argue that if the enzyme gets really negatively affected, um, it could be because of it unfolding, but unfolding really just happens like, when you like denature something when you unfold something, you break that tertiary structure.
Yeah.
So yeah, so if you're just changing, aspartic acid to glycine, that's not enough to that's not nearly enough to cause it to unfold. But yeah, D says, at least for the second half, less substrate needed to reach it is consistent with decreased Km values. And yeah, the Vmax, if the Vmax is lower, that could explain why the Km values are lower. So, so yeah, going into this, knowing that Km is inversely proportional to affinity is what will help you, particularly for this question.
Mhm.
But you did a great job in the buzzwords, knowing all that stuff. So good job.
All right. Thank you.
Mhm.
Um, okay. But like just to reiterate, like the Km can decrease and Vmax can still stay the same, technically, sometimes.
Theoretically, you're saying like if the Km could decrease and the Vx stays the same?
Yeah. Is that possible?
Theoretically, but that certainly wouldn't be an inhibitor then, right? Because that would enhance
Oh,
that, and maybe that could be
yeah, yeah.
what a coenzyme can do, or
Mhm.
some like a coenzyme, a cofactor, uh, something about the maybe the pH, certain things like that can happen. But ultimately, you want to see that a decrease in Km means an increase in affinity of the enzyme to the substrate. And if we're talking about inhibitors and we have a decrease in Km and no change in Vmax, that certainly wouldn't be an inhibitor. It would because the decrease in Kmax on its own, Km on its own is good for that, you know, enzyme.
Right. Yeah, this also,
Hmm.
um, yeah, I mean, yeah, so ask which solution component will have lowest concentration and the kinetic assay to describe. Okay. Lactate. You convert pyruvate to lactate, so this would not be a choice. Then you're left with ADP, ATP, NAD plus. They said the reaction is monitored by decreasing concentration of NADH. That means there will be more NAD.
Okay.
So then it would be between ADP and ATP. Um, and so I guess here for pyruvate kinase, it goes from ADP to ATP. So would the answer be then B?
Yep. Did you choose C?
No, I actually got this right.
Okay. Yeah.
I just forgot that I did.
Yeah. So that is key to what we said about this being an example of a kinase that removes a phosphate from a substrate.
Mhm.
Yep. And gives it to ADP. Yeah.
Okay. I think this I got wrong. So, which solution components are oxidized and reduced during the enzymatic assay described in the passage?
Okay.
So,
We can eliminate two right away, right?
um, okay. So we can eliminate this.
Um,
Wait. Sorry. I meant I meant this because it was the ADP ATP one.
yeah, because the dehydrogenase is the one that is redox. So we're not going to deal with PEP is the kinase reaction, not the redox one. So yeah, so it'll be
Yeah, so what I missed is the fact that they were converting pyruvate to lactate, but I thought that for some reason I thought that pyruvate to lactate is NAD to NADH, even though literally right after it said this. But
yeah, it does say it right after, but I guess it doesn't explicitly say, you know, that that this is exactly that because but yeah, I think understanding from metabolism is that yeah, the entire point of making NADH and FADH2 is it's like you're trying to save up on that so that when you meet the electron transport chain, you can give it to them. If you're never going to meet the electron transport chain, there's no point in you saving up NADH or FADH2. In fact, it makes more sense to trade that for NAD plus because glycolysis requires NAD plus as a reactant. So you can continue glycolysis by replenishing your NAD plus.
mhm.
So this is a big picture metabolic uh, pathway type of thing as well.
Okay. Um, this was the one other question I want to go over.
Yeah.
So the coefficient of viscosity of blood is directly proportional to the frequency of interactions of erythrocytes with the vessel walls. As blood enters small vessels, many erythrocytes tend to flow in the center of the vessel. Given this information, which graphic best describes the effect of vessel diameter on the coefficient of viscosity? So I made the proportion that viscosity is proportional. Wait, I can maybe write it. Like viscosity. Sorry, I'm a lefty, so annoying. Yeah. erythrocytes, right? But then I was confused because like it says blood enters small vessels, so it goes from high to low diameter. Many erythrocytes tend to flow in the center of the vessel, right?
Yeah.
And tasking the effective vessel diameter on the coefficient of viscosity.
Yeah.
So that's why I was a little confused. Because like the way I think about it, right? When you are going to the whole point of um like the whole basically they enter small vessels and they're small, so like from the way I remember it, it's like the whole point is to exchange oxygen, right? Like they wanna each interact with like the capillary.
Uh-huh. So yeah, those are all things. Um, when we have Tell me about both of these types of flow.
Well, the the bottom one is laminar, right?
Maybe.
Um,
So
the top one I don't really see.
so the top one is laminar,
Okay.
also known as streamlined, and
Hmm.
that is where you can use the continuity equation. You can use Bernoulli's equation. Now, if you remember, Bernoulli's equation is just conservation of energy applied, volumetrically to the fluid, right?
Yeah.
Now, if you remember, the
Can I stop you real quick? So, because I had a question on this before,
Hmm?
and they literally, it was on Blueprint. They showed the top one and it was wrong. Like, because I'm used to knowing it as this image. So, because like
Yeah.
that's why I'm confused because the like one of the like those two were both choices and ask which is laminar. So, and the bottom one was correct.
Yeah. So you're gonna still have so laminar just means like a straight line.
Hmm.
Okay. So and when you're comparing okay, so there's kind of like three things here. So first of all, Bernoulli's equation is conservation of energy applied to the fluid. And what do you remember like the difference between a conservative force and a non-conservative force?
Um, Conservative force cares about friction.
So yeah, you're close. So conservative means energy is conserved, and non-conservative means energy is not conserved. Some of it is lost. And the best example of a non-conservative force is friction, because friction involves energy being lost to the environment in the form of heat, right?
Mhm.
Now, friction doesn't have to be called friction every time. For instance, the resistance of a wire um, is also essentially friction. Now, viscosity can be thought of as friction between, let's say, like the layers of a fluid. Okay. Now, the difference between an ideal fluid and a real fluid is viscosity. Ideal fluids don't have a viscosity. Real fluids have a viscosity. So this top one here is an ideal fluid without viscosity. So all of the lines are like of equal length. But once you input viscosity, into it, it's now no longer an ideal fluid, but a real fluid. And that's why and this type of bowed shape is because the fluid that is touching the walls is producing friction against the walls, therefore flowing slowly compared to the center,
Mhm.
right? And turbulent is when you have, those whirlpool like eddies, right?
Mhm.
And turbulence, by the way, is inversely proportional to viscosity. Because if you had viscosity, you would have more friction between the layers, and it would be hard for it to like turn or swirl around. So the image that you showed me, right, is true, and the reason that they used this as the picture is because turbulence can only exist for real fluids. And therefore these are for real fluids, whereas this is for an ideal fluid.
Mhm.
So so that's why in the picture that you showed me, they showed laminar flow as this bowed shape because it's talking about real fluids.
Right.
And real fluids are real because of viscosity. Okay.
Mhm.
All right. Now that we have, so now yeah, it should make sense why, well, the difference between an ideal fluid and a real fluid is viscosity. And if you have a viscosity, you're going to get this flow, which I would call, I mean, sure, we can technically call it laminar flow because it's straight lines. And especially in contrast with turbulent flow, which is not in straight lines, it's like whirlpools, swirls. But we can also, I would think about it like this. I would think about this as Poiseuille flow, because Poiseuille's equation describes the laminar flow of real fluids, whereas Bernoulli's describes, or the continuity equation describes the laminar flow of ideal fluids. Okay.
Mhm.
Now, for this question, they're saying that the coefficient of viscosity in the blood is directly proportional to the interaction of the blood cells with the vessel walls, right? So what that means um, is that this coefficient of viscosity goes up the more interactions the fluid has with the walls of, the vessel. And then they say as blood enters small vessels, many erythrocytes tend to flow in the center of the vessel, right?
Mhm.
So I'm going to use green. This is the center, right?
Mhm.
Which is faster because it's the furthest from the walls, right?
Okay.
So what we're looking for then, right, is so basically if we want to figure out this coefficient of viscosity, which is a proxy for interactions with the vessel walls and diameter, right? We should see, oh, and then they're saying in a small vessel, it flows in the center, which would mean in a larger vessel, the erythrocytes would flow further from the center and closer to the walls. And if it's closer to the walls, we have a higher coefficient of viscosity.
Mhm.
So our coefficient of viscosity would have a direct proportion to the size or the diameter of the vessels.
So I just I just realized something.
Yep.
Is this potentially does this have anything to do with like the equation delta P pi to the fourth power over 8 NL and coefficient of viscosity is Reynolds number and diameter has to do with radius?
Well, so for the Reynolds number, that's going to be an inverse proportion to the viscosity and a direct proportion to turbulence. Um, and then for the Poiseuille's equation, um, the flow would be proportional to the uh, yeah, the radius to the fourth power. But here they're really just telling us, and yeah, so Basile is what you'll use to describe real fluid, aka a fluid with, viscosity. So that could be related, but here they're really just kind of telling us, they're saying that this coefficient of viscosity is proportional to how much the the blood cells interact with the walls.
Mhm.
And then they tell us the smaller the vessel, more erythrocytes flow in the center, meaning away from the walls. So we can then say if the vessel is larger, more erythrocytes will be on the sides interacting with the walls. So that means this coefficient of viscosity, which is proportional to interactions of the red blood cells with the walls, goes up with the size of the vessel. So the coefficient of viscosity should be proportional to the diameter of the vessel.
Okay.
Yeah.
So real flow and wait, no. Turbulent and laminar flow are both real flow,
So
right?
laminar could be describing ideal as well as ideal here, real here. Laminar just means streamlined, and you can see that the arrows are in a straight line for both. So they're both technically laminar, but it's just that if we have an ideal fluid, the laminar flow will have all of these arrows like equal, whereas the real fluid would have the bowed shape due to greater interactions with the walls of the vessel.
Mhm.
Mhm.
Okay. So if we have laminar flow, the ideal fluid will have all the same like length arrows, while real fluid will have friction, so the arrows differ.
Yeah, and they'll go faster in the center.